All right, I don't want to wait too long to get started because we do have a lot of good stuff to cover. So we are recording this, so might as well just get going if that's all right with you, Peter. Welcome all of you who have joined us so far for another installment of our Lunch and Learn webinar series. Although to accommodate our speaker today, we're having a late lunch while he is having breakfast. It's 7 a.m. on Tuesday morning, November 17th there. Pretty weird, huh? Few housekeeping items. Thank you all. I can see you're putting your computers on mute. Please use the chat or question and answer function to ask questions at any time during the course of the presentation, and we will leave time at the end for plenty of questions and answers. And I'll be monitoring the chat and questions as we go along. So hopefully you can sit back and enjoy some big picture discussions this morning, or this morning for Australia, this afternoon for the United States. So thanks again for joining us. We're going to learn how Australia is managing its biosolids, and I think we can learn a few things from them and our presenter today, Peter Hillis. I'm going to let Peter introduce himself so we can get right into it. Ladies and gentlemen, Mr. Peter Hillis.
Thanks, Janine. So just for your benefit, I did wear the same clothes as in my photograph because I've got a beard now, just so to prove it was me, and I've changed my glasses. So I'm Peter Hillis. I'm a fellow of the Royal Society of Chemistry, and I have a Master of Philosophy in Water Science from Cranfield University in the UK. I've been in the water industry about 39 years and really only worked for a small number of businesses. The first one I worked for was United Utilities, which is a large water utility in the northwest of England, which services about 8 million people in the sort of Liverpool, Manchester area, for those people who are familiar with the UK. And then in 2011, I worked for the American company AECOM, and I came over to Australia to work for them. And then the end of last year, I left AECOM and set up my own consulting business, PH2O. And I also at the moment am working for a biogas development company called Utilitas, and you'll hear a little bit more about them later in the presentation. I guess one of the sort of things to think about is why is this Englishman in Australia talking to us about biosolids, and how did I find out about Nebra? So I did a project for a company called Southeast Water here, and that was really looking at chemicals of concern, and I came across Nebra and the work they'd done on PFAS, and so I joined Nebra, got to know Janine, and I'm sort of familiar with the work that you guys have been doing, the struggles you have with PFAS and things in particular. So that's me, and that's how I got to, I guess, presenting to you today. What I want to talk to you today in terms of the Australian context on biosolids is sort of breaking it down into the various aspects, I guess, of the biosolids cycle. So this is about production of biosolids. That's both quantity and I guess in how we produce biosolids, the classification of them, and then the regulation, which are inherently linked, the exploitation of them, and really that's really what we can do with our biosolids beneficially, the augmentation of that, and that's really a lot of work around how we can look for synergies in biosolids and other organic waste materials. The realization then is how we then can realize projects, and then the circularization is, I guess, what we're all striving for. I always think that actually the water and wastewater industry has been at the forefront of circularization, just inherently because what it does, it takes material, cleans it and returns it to the environment from a wastewater perspective, and then that product or water is returned and reused in a I guess a macro circular way rather than a micro circular way. So in terms of production, so Australia produces about 370,000 tonnes of biosolids a year, and this gives you an idea of what happens to those biosolids. So As you can see, the majority are reused in agricultural purposes, some land rehabilitation, some for composting, and then a little bit of landfilling, a little bit of stockpiling, small amounts still discharged to the ocean, which is still allowed, and some other minor uses as well. And then in terms of, I guess the other thing is to say in terms of production as well is obviously the majority of biosolids are produced from secondary processing. There's very little primary biosolids production in Australia, a lot of extended duration plants, which again presents some problems in terms of processing and also the value, inherent value within the biosolids. So you know, the more we process our wastewater in terms of aerobic treatment, the less inherent value biosolids has. I've been involved in a little bit of work looking at the real benefit in enhancing carbon capture at the front end for exploitation purposes, and then looking at trying to minimize and reduce the amount of secondary treatment and secondary biosolids that we use. But that's a whole different story, I guess. In terms of classification, this is a very simplistic approach in terms of, you know, A, B, and C. And it gives you an idea of the sort of equal split roughly between Class A and Class B, but it's not that simple in terms of how biosolids are classified. So Australia, very similar to the United States, is a federalized system, and each of the states has it sets its own rules and regulations. There's no overarching federal rule associated with biosolids. Each of the states has set its own rules and regulations or guidelines. And a lot of them do refer back to the US EPA, I think 503. So there's a sort of common starting point, but then each of the states then has interpreted and modified it based on its own local situation. And I think that's probably very similar to what happens again in the US, where the states overlay their own needs and requirements on top of a baseline set of rules. So I quickly just wanted to step you through the regulations. So there's various state guidelines, and they're mostly classified in two levels. Treatment, so that's really about the sort of vectors and pathogens, and contamination, which is all then about metals, chemicals of concerns, and I guess there will be ongoing emerging contaminants as well. And obviously the classifications that are based on the level of contamination and the level of stabilization, and obviously stabilization is determined by the level of treatment. So quickly walk you through each of the states just to give you an idea of, I guess, some of the challenges of trying to work in the biosolids industry in Australia across state lines. So New South Wales, the Environmental Protection Authority, which is, I guess, different from the Environmental Protection Agency in the US, last updated its biosolids regulations in the year 2000. And it basically has three stabilization grades, A, B, and C, and they're driven really by the degree of thermal treatment. So higher temperature, certainly greater than 50 degrees C for a period of time, takes you to stabilizing grade A. Grade B is fairly traditional around anaerobic digestion, aerobic digestion, again with parameters around the operation of those, and even lime stabilization as well. And then stabilization grade C is if you don't meet any of the above two, then you're stabilization grade C. And then there are four grades of contaminant, so A, B, C, and D. And again, even sneakily, they sneak in a contaminant grade E at the bottom here. I don't know if you can see that, but again, it shows you that there's a sort of matrix approach to it, dependent on the pathogen load and also the chemical load as well. But you see, most of them are fairly familiar things that you'd expect in terms of heavy metals and pesticides, herbicides, PCBs, things like that. And then they also then give you a summary of how you can apply that based on the what you do in terms of the classification as well, and the approval source. So all these regulations, like most biosolids regulations, are available on the internet through the website. I would recommend, if you're interested in learning more about Australian regulations, the Australian New Zealand Biosolids Partnership, which is anzbp.com.au. That gives you hyperlinks to all the Australian and also some of the international standards as well. So it's quite a useful resource, and also there's some freely available publications as well that may be of interest. So Victoria, which is where I'm based, so we have a Environment Protection Authority as well, and our biosolids regulations were last updated in 2004. And again, it's classified in treatment and contaminant. So we have a T grading, so treatment grade 1, which is summarized here. And again, that is really about higher temperature or longer duration. So example, we've got long-term storage of sludge or biosolids if it's digested, dewatered and stored for 3 years as well. So again, there are slight variations between the states in how they're classified, but we have a T1 grade, we have a T2 grade, this again is sort of higher temperature digestion type processes. And finally, our T3 grade, and even and only anaerobic digestion only makes it into the T3 grade as well. And then we also then have a contamination. So we got T1, T2, T3, and C1 and C2. So again, we've got this matrix approach based on how you produce your biosolids, and then what the contaminant levels are. And again, heavy metals and pesticides and PCBs. Not an exhaustive list, as you can see, but these are the only ones that are in the regulations at the moment. I mean, there is an ongoing review of regulations, but I'm not sure, from a priority perspective, where that sits at the moment. Queensland has what's called its End of Waste, and that was published in 2011, and that's from a different government groups, the Department of Environment and Science. And again, they have an AB classification. Again, not going into the detail, but again, just to explain. And you see anaerobic digestion. Aerobic digestion sits in grade B, and grade A tends to be high pH or high temperature treatment of biosolids. They also have contaminant gradings A, B, and C now as well. So again, it's that approach of mixing and matching how you produce your biosolids and what the contaminants are. And I guess of interest here is that they were the first state to actually put in some trigger values around the PFAS trigger level. So here you can see the trigger values around that. Again, there's a bit light on detail, but you can see, well, it's I guess a clear indication that PFAS is now becoming of concern over here. There's a lot of PFAS contaminant being found in some groundwaters and wastewater. So, but some states are ahead of others. So again, there's no real national agency coordinating this. It's very much driven by the states in terms of biosolids. So Western Australia in 2012, in the Department of Environment and Conservation, so they have 3 contaminant grades, C1, C2, C3, but they now have 4 treatment grades, P1, P2, P3, and P4 as well. So again, not going into the detail, but I guess just again trying to sort of paint that picture of the sort of different ways that states have embarked on the biosolids regulations. And the most recent biosolids state to update their biosolids is Tasmania. They updated in June 2020, and they have an Environment Protection Authority that looks after this. And again, they've got stabilization grade A, and again, what that looks like, contaminant contaminant grades A and B. So again, probably some of the simpler in terms of the classification. And again, the interesting thing is even within the country, there are very different, sort of subtle differences between some of the contaminant concentrations here as well. And then, interestingly, again, so there's that matrix approach for Tasmania that says that this is what a class 1, class 2 is, and then what they then determine the difference between what they call a sewage sludge and a biosolid. So, and again, this sort of matrix gives us what we can do and what additional requirements are, and then sewage sludge is a controlled waste. And so if you're not meeting either an A or B grade, then it becomes a controlled waste, and you end up, I guess, falling under different rules and regulations. They also do put a statement in their regulations recognizing PFAS as well. And so they've really got a watching brief on this. So they're in a monitoring assessment phase as well, and really trying to understand whether or not they will need to, I guess they will need to regulate in the future, but at the moment it's very much a watching brief. So that gives you a sort of overview of where regulations sit in Australia. And I'm guessing it's not a lot of differences. There's some complexity in how people have classified it, and some are more complex than others. But generally, you know, in terms of getting or producing biosolids that are suitable for beneficial reuse, there's a little bit of a common theme and a real strive really to produce higher quality and higher class biosolids moving forward. I think that there'll be a push also from the end users of biosolids as well, but generally there's quite a good community engagement between the biosolids producers and the biosolids end users at the moment. So and there's lots of collaborative work and research going on. Local university here in Melbourne, at Royal Melbourne Institute of Technology, has just set up a Biosolids Centre of Excellence, and their role really is to try and coordinate biosolids research throughout Australia. So that's that. So now getting into exploitation, and it's interesting in looking at this, and I had a chat with Janine, was really that we're in the 21st century, still sort of exploiting 19th century technology, and not to diss the people who invented that technology, but I guess the question is that the right approach for where we are in the modern world and what we're trying to achieve? So we tend to be relying on active flated sludge and its variants. That might be an early 20th century innovation, but it's high energy consumption, which is what we're trying to avoid. Produces secondary sludge, which doesn't digest particularly well, and that's been known for a long time, but we still continue to do that because our processes are very much not driven around the biosolids we produce, but more about the quality of the effluent that we produce. And we're still designing anaerobic digestion plants that maybe we could say are inherently suboptimal. And part of that is the inherent conservative nature of the industries, that we're always adding a bit here and there from an engineering perspective. We're always adding a bit of contingency, and the question is, does that do more harm than good sometimes from a process engineering point of view? Overall, the design hasn't really evolved much, and I guess it's all designed around cost rather than, and I think that's a historic approach. I think now we're looking again more around how we design and how we look at the cost in both the economic and financial aspects of projects. And we do have a whole heap of legacy, but even new plants, if we go down the AD route, in order for them to become more effective, they do require sort of pre-treatment built on to improve performance. And one example of that is a sort of thermal hydrolysis approach, where we might still design a thermal hydrolysis with a conventional digester at the back end. And maybe things aren't designed for modern drivers around energy and carbon, and design these things to recover value as well, and how adaptable they are to change. So this gives you an example that this was actual patent produced for anaerobic digestion in 1900. And actually, if you think what it says there, we put sewage in a closed covered tank, generate gas for the purpose of heating or obtaining motive power in explosive motors. So not a lot has changed there. I mean, maybe pushing the bounds of credibility a bit here, but generally we put our sewage sludge in a covered tank. We've improved the performance of the tank in terms of how we feed sludge, how we mix it, how we control solids retention times and hydraulic retention times, but the basic principle hasn't really changed. And interestingly, in the sort of similar period, the Wright brothers took the first, I guess, manned flight in northeast USA, I believe. And so if we look at what's happened since then and now, is that, and again, pushing the limits a bit, but making the point that, there's been, we are able to make huge technological leaps if the drive is there to do that. And certainly, obviously, for air travel, big drive, big incentive. But maybe for how we've dealt with biosolids, we've dealt with the sort of some inertia and inherent conservatism in the industry to really focus on paradigm shifts in technology. Now, I know there are significant changes in technology, but I guess the lesson for us in the water is how we exploit and how we rapidly adopt and adapt to new technologies, and what are the barriers to entry of technology into our market. And so in terms of the 21st century exploited biosolids, there are opportunities in technology, and there are technology that on the face of it seem disruptive, like thermal hydrolysis, but been around for a long time. I think there are over 70 plants worldwide using thermal hydrolysis to pre-treatment to anaerobic digestion. Whether those plants are optimal, designed, and making the most is a case-by-case basis. But now also, we've now seen interest more and more in thermal technologies in biosolids applications, in gasification and pyrolysis. Now, there are some limitations to these technologies, dependent on the quality of the biosolids going in and the ash content. So they do have some limitations, but these higher temperature thermal technologies are able to deal with some of the contaminants like PFAS. May well start to become more and more interesting. And again, it's the picture of looking at what are the byproducts from these processing technologies again, and making sure that when we're adopting these technologies, we're taking a bit more of a holistic view and a circular view in making sure that we're reusing all the outputs and ensuring that our inputs match the process. And then co-digestion is the obvious one, and lots of examples in the US and Europe around co-digestion. Fairly new to Australia. There's a lot more interest in anaerobic digestion and generating biogas from organic waste, and also the combining of wet organic waste with biosolids within water utilities. So Sydney Water, Melbourne Water, Yarra Valley Water are all have active co-digestion projects at the moment. The other opportunities are around centralization as well, and I think one of the barriers historically has been utilities in a sort of fragmented market. I think a little bit like rural Australian parts of North America, whereby certainly small regional plants don't generate sufficient quantity to justify investment. So one of the things we've been looking at here is how we can look at those synergies of centralisation and economies of scale to make projects more viable. And also an adaptive planning approach. And what that approach is how do I make sure that my investment that I'm making is strategic and long-term? And how do I think through that process? And there's obviously always the risks around opportunities, and all very familiar with emerging contaminants or real contaminants, and certainly emerging ones, and what's the world going to do about microplastics and other chemical concern. And even at the moment, I mean, lots of headlines of COVID in sewage, and people, now monitoring sewage quality to look at COVID-19 hotspots, and lots of tracking and tracing around that happening, certainly in Europe and in Australia, where all major sewage influents are now monitored for COVID to see if how the tracking cases. And again, once the public gets that perception that what ends up in their sewage is a direct consequence of what they've done, and how that then pays at risk the sort of circularization of everything we do, from recycling water to recycling biosolids. And then also, with more complex projects, become more complex contracts as well. So when we're doing centralization and trying to work across multi-agencies, for example, then contracts can get in the way, negotiations can get in the way. And then also competition, particularly in the co-digestion and organic waste market, is that competition for that waste stream will start to affect the financial viability of projects as well. So co-digestion projects with biosolids are at the moment commercially on a knife edge, you could argue, and competition. What you don't want is competition to kill that. So the important thing around that is the security, and again comes back to the concept of long-term reliable contracts for imported organic waste, and how sustainable those contracts are. Ginny, is it anybody want to ask any questions, or are we okay?
No questions yet, Peter.
Cool.
Just keep an eye on the time there.
Yeah, no worries. Okay. So adaptive planning. So this was this idea of really looking at how you produce your biosolids. So this is the idea of primary and secondary biosolids, how we exploit them. So where's the value in the biosolids, and what is it that you want to do? If you want to extract the energy out of them, then you want to enhance the amount of primary material that you collect. And then if you want to enhance that, it's how you augment those with imported organic waste material, and that'll be driven by your local factors. And if the majority of organic waste material is dry organic waste material, that might make a decision to move to a thermal process rather than a wet processing system. And then how do you, I guess, really develop standalone organic waste to energy facilities independent of biosolids as well? And finally, the production of valuable ones. So the idea behind this adaptive planning approach is really to look at the end-to-end picture, and look at all the decision points within that, and questioning, when I make that decision, what does that mean for my long term, and how does it fit into the external factors? So here we're looking at different scenarios and different externalities that will impact what we do. And that is very much dependent on the local factors. And also, this is a case study that I was involved with. It was, these black dots represent a number of wastewater facilities in a particular region. And we looked and found that 80% of the waste activated sludge is produced in a fairly tight band. But none of these sites have sufficient biosolids to sort of have a standalone facility. So this was the idea of the centralization, and looking at what the synergies and benefits from centralization are, and then how that doing that ties into the wider picture of what you're trying to achieve from both a business or company perspective, a community perspective, an environmental perspective, and all those other factors that start to drive you. And really, again, it's really look at this sort of inputs and outputs. So what I've been trying to do is really look at the process a bit of a black box initially, and not make a decision driven by technology until I understand what my inputs are and what I'm trying to do in terms of my output. So what do I want to produce? And that will be driven by a whole heap of local factors. Do I want to produce biogas, biomethane? Do I want to produce a biofuel? Do I want to produce heat? Do I want to produce a biochar? Do I want to produce a fertilizer product? All those decisions are really made, and then the idea is you've got a raw material, you understand the marketplace you operate in, and then you identify what the right technological approach to achieving that is in the most economic manner, rather than starting with the technology and really making that technical decision as late in the day as possible, such that you really tailor that to your end needs. So this is sort of again a model of based around anaerobic digestion here, and that was maybe a first decision point along the planning route, is that we decided to go to anaerobic digestion. But then when we look at what's our long-term approach, we get a much more complex picture again of, what do we do in the future if we start off with our biosolids and then we look to importing wet organic waste and other waste materials. How do I ensure that making that first decision to anaerobic digestion, how does that integrate with a much longer term plan and a more complex plan to a more, I guess, productive outcome? So I don't want to get into the detail, but that's that approach of how in an adaptive planning you start from a first decision, but with in mind what your ultimate decision looks like. So that first decision to go for anaerobic digestion here fits, and how does that fit into a longer term plan? And so this was, I guess, a summary of sort of, we've got our biosolids, we get to a crossroads and we have decisions to make. We can stay where we are, we can go down a liquid processing route, we can go down an anaerobic digestion route, or we can go down a solids route. But, like the scarecrow, which is the right way to go? And depending on where you are and I guess what your legacy is and the assets that you have, there are opportunities to sort of leapfrog. The analogy here is in Vietnam, when they decided to implement a countrywide phone system, they'd never had a pearls and wires system. So they jumped straight to a completely mobile technology because they weren't hindered by their legacy. And one of the issues we have is that our legacy of investment and assets can sometimes really hinder what we think and what we do. So if we don't have that legacy, we can make much bolder decisions and jump forward. And certainly that's the case now with these thermal processes emerging, that there are opportunities now to circumvent the traditional sort of digestion-based route and go to a more solid or thermal route for processing. So, and that which way to go is going to be driven by a whole heap of factors. So that sort of summarizes that idea. That so just wanted to move on to, I guess, in terms of what the company I'm working for, Utilitas, is doing in how we're trying to move the biosolids and biogas industry forward here. So I've talked about sort of legacy issues as well, lack of policy and incentives. We've had a up and down relationship with carbon and carbon pricing. Some states here have taken a very aggressive approach to carbon neutrality. The state I'm in, Victoria, has basically told all water utilities they have to be net zero carbon, and that includes scope 1, scope 2 emissions by 2030. So, state governments, depending on, I guess, their political persuasion, are really driving quite aggressive agendas as well. So that's really been some of the impetus behind this sort of drive. And also within that, though, it obviously comes inherent risks, and people always, I guess, balk at the idea of being the early adopter. But how do you move past that as well? There's obviously lots of issues around access. So I'm involved in a biogas to grid project at the moment, so converting biogas to biomethane and injecting it into the grid. But there's a whole heap of barriers to there, and driven by regulations around how we monitor and maintain gas quality, all the standards, and all these things overlay the price and the sort of financial viability of projects as well. And I guess the other thing really is our traditional approach in the water industry to how we engineer projects is again very conservative. And if the financial viability of some of these projects is borderline, the more we engineer them, the more likely they are not to go ahead. So again, what we've been trying to do is look around how we can de-risk projects, review how we engineer projects, engineering them maybe to a shorter life, so again they become more adaptive to the technological changes as well, and trying to sort of get a more efficient approach to the typical engineering, procurement, construction and management of them. So what the solution that Utilis has come up with is based really around biohubs and the sort of regional biohubs. What we've sort of, or what they've looked at is staying out of the major metro areas and looking really at synergies in community ones where, I guess, as I said earlier, it's more difficult to make projects viable. But the idea is around creating regional biohubs. Regions have two things. They have biosolids, but they also tend to have lots of organic waste material, whether that be wet or dry, and trying to, I guess, package that together in a delivery model whereby we would build, own, operate the plant and have long-term contracts based on waste materials, and also market the resources, and then a commercial arrangement around gate fees and the benefits of reduced energy or reduced carbon to the utility. So why a biohub? Well, lots of good reasons. Biohubs, one, create jobs. They create they can be I forget what it's gone. They can initiate or be the sort of catalyst for investment as well, and around the biohub, because it's using utilities, using services, but also generating resources. It can be a sort of stepping stone to attracting a wider investment. So we can produce, we can produce better byproducts, we can produce high quality products, we can attract other industries as well. And also biogas as a fuel source, lots of benefits around that. And also, we can, with technology, and I know this is anaerobic digestion, but there are opportunities now to get multiple feedstocks with multiple technologies to get multiple outputs in terms of types of products, but whether they be fuels or reusable or agricultural type products as well. So generally what's involved with this is that there's always we'll look at developing the biohub, again based on the regional requirements, looking at the market for inputs as well as the market for the resources as well. And what Utilis has done, it takes that approach of taking all that off the utility, taking ownership of that, and providing both a pathway, funding and technologically to the realization of a biohub as well. So we do the development, we do the delivery, and the asset operation and maintenance as well, and all in a very much a sort of open and transparent partnership model. And the idea of that is that we de-risk the feedstock. So the idea is that we own the feedstock risk, and that's done by ensuring that we fully understand the feedstock marketplace, and trying to tie in with what we call anchor tenants. So what anchor tenants can be a utility with their biosolids, or they could be farmers, other industrial waste producers. We certainly know what to do with biogas and to create the best benefit of that and the flexible approach to that in terms of what we can produce from that. We're working with companies now looking at producing hydrogen from biogas, as well as biomethane, as well as compressed natural gas as well for fuels. And then finally looking at how we monetize carbon value as well. There will be a global market in carbon at some point, and really how we plug into that. And then the finally is what we've developed, which is how we de-risk technology. We're developing what we call the Incubator Site. So this is a place called Bundaberg in Queensland. It's quite a unique site in that it's got a deep water port. It's got a huge agricultural hinterland. It's got a reasonable sized town. It's got good links. And it has a disused wastewater facility that we've taken ownership of. And the idea behind that is we're going to create a precinct where we allow technology providers to demonstrate their technology at scale in a commercially viable manner to sort of take away that early adopter risk from utilities and partners. So people could come look and see and feel the technology and actually look at the economics of it and look at what we generate, what we create. So this is an exciting innovation. It's only just been launched. We've already got quite a number of tenants, and that will again looking at a hydrogen hub, looking at some conventional, but looking at thermal processing and looking at traditional things like composting as well. So it's not. It's really the idea is to give a portfolio of technologies whereby people can come and see what's possible at a single site as well. We've got a number of delivery partners as well that we're working with on that. So the Regional Council, Scania, which are a large truck manufacturer in Scandinavia, again, we'll be looking at producing compressed natural gas for them, and Veolia is an operating partner as well. And the number of partners is growing quite exponentially. And the idea is behind all this is where Utilitas sits in as really us as the biogas or the Biohub developer, and then bringing the right parties together to develop that. Okay, so that I think was 44 minutes, so not too bad in terms of time.
No.
I'll just stop sharing.
Sure. And
okay,
actually,
sorry.
Don, if you wanted to unmute, you can just ask Peter your questions yourself if you'd like.
Sure. I can't remember what my questions were.
So I can't remember the answers, Don.
You were looking for a rule of thumb.
Oh yeah, is there a minimum quantity of biosolids where you would think that an investment is feasible?
Well, it really depends what you want to do. So I've recently been doing some work with a Canadian company who provide mobile gasification plant,
mm-hmm.
and they have a plant that does about, let's say, 1,000 dry tons a year.
Yeah. Right.
And that cost of that is under $1 million for the piece of kit. It comes in a 40-foot container. So what that says, so you can get technology equipment off the shelf available. It's just your approach and the approach to having, what looks like a pilot plant, but as an asset. I've been also, there's a company, I think they've actually have some technology over there. There's a company called Waste Master, which I've just kicked off a project with them. So they have I think it's a 500, I'm sorry for talking in a metric, but that's all I know, a 500 kilograms a day system. And we think that they can process, maybe at one ton a day through one wet ton a day through a single unit in 24 hours. And within that, they'll get rid of 80% of the water, liquid, and produce a stable product that is pathogen and odor free. So, there are these sort of small niche technologies. This has been used on a number of waste streams, supermarket waste, but we're now looking at the first biosolids application. And the idea, the concept behind it was for small sites. We could put one of these units on. We load it up on a daily basis, and then because we produce a material that's stable and dry, you can actually store it on site as well. And it actually uses, do you call them wheelie bins? The bins on wheels, your garden waste bin.
Wheelbarrows?
Yeah, wheel bin. Yes, yeah. So you basically wheel your bin into the machine, it tips it up, it processes the biosolids, and it dumps it in another bin at the other end. So there are sort of smaller scale opportunities and options. It's going to be driven. If you wanted to do a sort of a big biohub with anaerobic digestion, then I think you're probably looking at maybe 40,000 wet tons a year, maybe that sort of. But I think the world is becoming a little bit more decentralized in some respects in terms of the technology. So, bit of a horses for courses, but I would say the old rule of thumb where people would say 50,000 equivalent population before you could do anything, I think those days are sort of now diminishing. Mm-hmm. But I do think there are synergies for centralization on that. If you can find partners, then economies of scale are just a fact of life in some aspects. But there's micro stuff that can be done, undoubtedly.
Right.
But your technology has become a little bit, bit different.
Sure. The region that we're a part of consists of a lot of small municipalities that they don't produce enough biosolids to really warrant the. So the big push is as a centralized regional plant, but that takes a lot of cooperation. So that's another.
Undoubtedly, yeah. I mean, but so what we think we're looking at this waste master technology is that we have localized sort of stream stabilization, but then that product can do a number of things. You can apply it directly to land, or you can anaerobically digest it, or you can thermally treat it as well. So it gives you a flexible approach to the end market. But if you're going to start to treat it, then you're going to have to take it to some sort of central processing facility, I would have thought, if the plants are really small.
Right.
But listen, keep an eye out for. I'll give Janine an update on this Biosolids Waste Master trial that we're doing. It's only just kicked off. We won't probably have the results sometime early in the new year. But if that works out the way we think it will, then it could be quite disruptive in terms of helping us deal with, at least with biosolids stabilization and storage.
Yeah, that sounds good. Thank you.
The other thing about it actually is that it also reduces the time for anaerobic digestion by about 50% as well.
Oh wow.
Oh.
Yeah. Another question we had from one of our Canadian attendees is what triggered your decision to monitor for PFAS in soil? Simply because it's a rising concern, or
pretty much. Yeah, so Australia, the PFAS debate in Australia started like most cases to do with water and groundwater contamination, and particularly associated with a lot of Air Force bases. So the Royal Australian Air Force has got a big problem with the contamination of groundwater and therefore land as well. And also wastewater. So we're finding then legacy issues of it ending up in the wastewater and then the biosolids. So, it's the same story everywhere, is that, you find something and then you follow the chain of custody and everything unfortunately ends up in the wastewater and then unfortunately ends up in the biosolids, like everything. It's a sort of inescapable fact and challenge that we live with. But I guess, we are at the end of the pipe, unfortunately, and we end up with all these issues to deal with. But yeah, same as everywhere, and lots of community pressure, lots of interest from the press as well. So that's all it takes, really.
So literally end of the pipe. Yep. Yeah, so I'm definitely very interested in following the progress of the Biohub and your experiments there. So I want to stay.
Yeah, we'll give you an update at some point next year, maybe. Yeah,
that would be great, and hopefully we're all. I know Australia's doing very good with COVID, so we can learn a lot from you in that respect as well. So,
so I've even got my my Australian Indigenous mask in the car as well.
All right. I don't see any more questions.
I do have one more, Janine. Just wondering, because of the climate change and the droughts that you've seen, is there a big push for water reuse? And
So we went through what's called the Millennium Drought, which sort of was in the sort of between 2000 and 2009. The whole country suffered a pretty severe drought. All states involved, and that pushed. There was a big push then around water security, and obviously three aspects of that. One is reduction in consumption, so big push to get water consumption down. So I think in the year 2000, the average Australian was using over 300 litres per person per day. So what's that? So divide by 4 to get into gallons.
Right, about 80 or 90.
Yeah, we're now push that down to about 150 litres per person per day.
Wow.
All right, so that was the first push. The second big investment was in desalination. So all the major cities basically took out an insurance policy, which was to build desalination plants. So all the major cities now have a desalination facility. Now, they don't always operate. So in Western Australia, in Perth, they're baseload plants now because they've had the most severe drought. But all the other, Adelaide operates maybe at about 20 to 30% capacity. Melbourne, they operate on an order basis, and those orders are based 12 months in advance, depending on climatic conditions. Same as Sydney. So there was a huge investment in desalination, tens of billions of dollars, but then also a big investment in recycled water as well.
Right.
And a big investment in recycled water guidelines, but not really direct potable or indirect potable, mostly recycled water for purple pipe systems or irrigation of agriculture or sports fields or community-based irrigation schemes as well. So, but big challenge like all those is the economics of water reuse and recycling as well. So that's a big challenge. So a lot of investment, but a lot of mothball plants probably you'll find as well. But you know, like all these things, there was a crisis. People responded in a crisis, and in that, you make some good decisions, you make some not so good decisions. But generally, I think where Australia is, it's obviously because it's got desal. You can make the argument, you know, for the major cities, water restrictions are probably a thing of the past, depending on how populations grow. But the bigger challenges are the rural communities, particularly inland rural communities as well. So recycled water, there's a big one. There's some, and I think what's going on in California and Texas and Arizona and those places is as good as what's going on anywhere really in terms of, you know, the research, the indirect and direct potable reuse. I actually did a project a couple of years ago in Antarctica with the Australian Antarctic Division, where we looked at a direct potable scheme for small communities. And that presents quite an interesting challenge because you actually find that the infectivity rate goes up. So therefore, the amount of barriers that you require, because the person-to-person contact is greater in a small community. So therefore, if one person gets sick, the transmission rate is greater. So therefore, you have to then apply more barriers in terms of your log removal as well. So that was quite an interesting way of looking at that.
Yeah.
So, yeah.
Absolutely. Thank you.
No problem.
Yes, thank you very much. That was very thought-provoking.
Okay.
And yeah, we'll want to stay tuned in to how you guys are doing and how you're
Yeah, well,
progressing. We are all dealing with the same problems, I think.
We are, yeah. And listen, as I say, a lot of how it's done is driven by things outside of your control, whether that be regulation, whether it be community perception, whether it be, a particular advocacy group, or whether it be the media. The important thing is to be in control of your destiny more than anything.
I hope so.
Yeah.
Well, if there's no other questions, then I'd like to thank all of you for joining us, and thank you, Peter, for taking the time and sharing your knowledge and some of the cool stuff going on there in Australia. Sure. And maybe we'll follow up again next year and see where you are with this.
Yeah. And anybody, feel free to contact me directly if you want to have a discussion online or any questions or any thoughts that come to you in the next few days. I know sometimes, questions could arise a little bit afterwards, but feel free to get in touch either through Janine or directly with myself if you make my contact.
Yeah, if you don't mind, then I'll share your email address with them when I send out the recording.
No problem.
All right. Thank you guys very much. Thank you so much, Peter. Thanks for joining us, everyone, and have a great afternoon. Have a great rest of the day, Peter.
Thank you. Take care. Bye-bye.
Bye-bye.
See ya.
Bye.
Bye.